Hi everyone, welcome back to this video series where we talk about introducing material phenomena in nuclear environments. So in the last video, we talked about quantifying and estimating how bad some of these material damage is by calculating some typical values of pKa's and how many pKa's or how many dPa's, displacements per atoms, are being generated. So, we know when let's say you have a neutron, it knocks onto a pKa, it's going to cause several other atoms to knock off, and it causes a lot of frenkel pairs. And what are frenkel pairs? Frenkel pairs are vacancy plus interstitial pair. Just to remind us, frenkel pairs are vacancy and interstitial pairs. So every time an atom is displaced from its position, the site where it's displaced from, there'll be a vacancy there, and this atom that is dislodged and displaced, it will end up as an interstitial somewhere else. Okay, so this zone, we call it a displacement spike. So this is called a displacement spike. And what happens to all these frenkel pairs? What happens to the frenkel pairs? Well, there are a few basic things that will happen. So I'm just going to summarize them below. So we'll separate them into the vacancies and the interstitials. Okay, so the vacancies tend to coalesce into small clusters. For a BCC structure, you have nanovoids happening. And for FCC, what happens is that you have stacking fault tetrahedra. I'm going to explain how we can sort of think of the process happening. May or may not be accurate, but it's a useful way to think how it happens, and you can remember why vacancies will cause this stacking fault tetrahedra. The other way is for vacancies to coalesce into large cluster. So they call it voids in this case. What about the interstitials? Interstitials will collapse into or coalesce into dislocation loops. Now, the thing is that for voids and nanovoids, it's kind of easy to visualize. Okay, you have vacancies which you can think of small bubbles in the lattice that will coalesce, they will join up to form bigger bubbles. It's a very easy thing to visualize. But for stacking fault tetrahedra and maybe this dislocation loops, it's a bit abstract, so we're going to go more into depth of how these things happen. So we're going to go into that. And one other thing before we start, we're going to take note of is that interstitials, they are less stable than vacancies. Okay? So imagine we have a lattice. We have a lattice here, and we have several closely packed atoms, and you have one interstitial here that is trying to squeeze its way into a very tight lattice already. Remember that the atomic packing factor for FCC is about 0.74. For BCC is 0.68. And there's barely any space left in these atoms, and when the interstitials are lodged into these interstitial sites, it's very unstable because it's already very tightly packed. Whereas for vacancy, the strain on the lattice isn't as much, so they are way more stable. Okay? And there is some mathematics behind this. Some people do a point defect balance, and this is available in Professor Olander's book. So this is got point defect balance. It's a very intensive mathematical treatment to this. So it's another lengthy derivation. I may or may not do this in the future, but if I do, I'll insert it as some appendix in the video. Okay, so starting off from what we were talking about before, we want to see what happens in this dislocation loops and in this stacking fault tetrahedra, because it's very hard to visualize. Okay, so we start with the first notion, first fact that interstitials are really unstable. They want to move around, they want to get into a more stable configuration. So when you try and jam pack these interstitials into one of the sites, it's causing a lot of strain on the surrounding atoms. So it wants to move around. How does it get into a more stable configuration? Well, one of the ways to relieve stress is what they'll form dislocation loops. And what are these dislocation loops? Well, there's a website with a nice diagram. I'll put it in the description below, a link to shows the mechanism, and it has nice animations. So it shows the mechanism for forming one kind of dislocation loop, which is called a prismatic loop. So I'm going to try and draw some of that in this video. So let's say you have interstitials. Here's something like this, a very cramped interstitial lattice. And well, from what we know about these locations, we know that it looks something like this. All right? Okay, where these are all the planes, and this is the extra plane being inserted in, and these are all the other planes, right? So these locations are pretty stable-ish as compared to an interstitial, because you can see a lot of them actually existing in the lattice and moving throughout the lattice from time to time. And some of them, yeah, they are stable, they stay in the lattice. So you can infer from that the strain is not so much on the surrounding planes as compared to the strain exerted by individual interstitials. So okay, let's say we have this plane. So I'm going to draw like 3 planes here. Okay, and let's say you have an interstitial here, an interstitial here, an interstitial here, and an interstitial here. And maybe we put one more here. So I'm going to color all these interstitials as a different color, just to help us try and understand what's happening. Alright, so first thing first, we know that these locations are pretty much stable, and these locations are like a extra plane of atoms within the lattice. So what does that mean? It means that these interstitials will try and form an extra plane in the lattice itself. So when this atom here, this one I'm pointing to here, is walking around looking for spaces to lodge itself in, it's eventually going to find itself lodged in here. Okay, this is the most stable. It can go to other places, but when it arrives here, it will not likely diffuse to other locations. Why? Because this is sort of an extra plane that's already forming. And when an extra plane is forming, that's when it will be more stable. So eventually, other interstitials that are walking around randomly, they call it the random walk. They are diffusing around randomly. Okay, they are diffusing around randomly, and then they find this location. Then they will start to join together. I mean, not just in a 2D manner, like this simple plane here. You can imagine they are forming a 3D disk of interstitials, which form a 3D disk shape plane. So let's draw this in terms of planes like this. So we have 3 planes. So the first and the second one, 1 and 2, they're like this, and then there will be an extra plane here, which are all these dark colored atoms. And then this is plane number 3. So this is kind of a side view. Okay, so you can imagine if as there are more interstitials, they will start diffusing to this extra plane and this thing will grow. You can notice the strain on the surrounding atoms isn't as much as, say, something like over here. So let's look at the top view. Okay. Alright, so that's a top view. So as I said before, this is like a disc shape. So I'm just going to put it. Almost looks like a black and white photo of a flag of Japan, but anyway, that's the idea, is that you have a roughly disc shape of extra plane over here. You know, all over here at the edge of the this extra plane, that's where the dislocations actually are. And this is what a dislocation loop kind of looks like. Alright? So that's the same can happen for vacancies as well. Though for interstitials, this is way faster. So for vacancies, you can form a void. Okay? Equivalent thing can happen, you can form a void. So you have something like this. Okay, so there's a void disk, which is, the proper name is called, again, a dislocation loop. So when this disk can start as a small void, and then when other vacancies join the void, it kind of grows. But at the same time, if an interstitial finds a void like this, it's going to make the void shrink. And if you have an interstitial and a vacancy, when the interstitial rejoins the vacancy, the damage is eliminated. So in effect, when the interstitial joins the vacancy, the bond is reformed and the damage is eliminated. Okay? Right, so we talked about vacancies forming a void disk, or rather the correct name is called dislocation loops. And well, how does it form a stacking fault tetrahedra? Let's say you have this kind of a disk, or dislocation loop, sorry. This dislocation loop inside a FCC structure. Okay? So I'm going to label it ABC. A, B, C, A. Okay? So this is one way to think of it. There is some strain here. There's some strain here, and what the FCC structure is trying to do is to minimize the strain energy, because there's strain here that's pushing atoms into this lot here. So B will feel this section of B, okay, this small part of B will feel like it wants to move down here. So it's going to move into here. Okay? And what we have after that? A, B, C, A. A, C, B. So this B will have this dotted line that's coming down. Okay? This is also B. And this is A here. And this layer is the same layer here, C, B, and A. Okay, so this B kind of moves down and to try to lessen the strain. And to lessen the strain, it's actually a slightly smaller chunk of B that is moving down to fill this void here. So this void here, this dislocation loop, it's a bit smaller than the dislocation loop over here. So you can imagine the same thing starts to happen. C is drawn into this part, so it starts to form here. Okay? Okay, anyway, yeah, so it starts to form here. So it moves down, and you can imagine the process keeps repeating until you have, let's say there's an extra layer B here. I'm just going to draw extra layer B. Then you have A. Okay. One more C, B, and A. So remember, you have a B here, I have a small section of C here, and a small section of A here. So what you have is this, well, this kind of helps to lessen the strain of the atoms, or of the planes at the bottom. And what you're left with is this small little point, and there's not much energy for it to attract atoms from this above plane up down into here. So these dislocation loops may not be circle, they're actually, you know, like triangle shape, tetrahedral shape, because that's the most stable configuration for an FCC structure. In BCC this may not be the case, but for FCC that's certainly the case. So what you have is this shape where at the bottom is a triangle shape, and each side is a triangle shape as well, so that it's a large triangle at the bottom, followed by small triangles, followed by smaller and smaller triangles, so that what you have is a stacking fault tetrahedron. So what's a stacking fault? Well, normally here, this whole plane here should be A, but instead it's half being filled by a B. This should be a B plane, but is filled by a C plane. And if you're not sure, please go and watch some of the videos. I'll put stacking fault. Watch some of the videos of what a stacking fault is. And this is one of the important defects in a FCC structure. So we have explained how a stacking fault actually occurs. And we know that vacancies can form either small or large voids. And while interstitials, just want to recap, the interstitials can usually form these dislocation loops. And some interstitials can join these dislocation loops. And in other cases, vacancies plus interstitials will join to eliminate damage. Or an interstitial can look into this dislocation loop that is caused by the voids to make it smaller, so the defect is being absorbed. So how does all this affect microstructure? And you see that with FCC, we have all these stacking fault tetrahedra. Let me divide this paper into 3. We all have all these stacking fault tetrahedra, and nanovoids will be for BCC. So I go with stacking fault tetrahedra, SFT. For BCC, we have nanovoid. But for both, we will have large voids. If the voids coalesce enough, there'll be large voids. And then for both BCC and FCC, we will have dislocation loops. Of course, some of the vacancies and interstitials will rejoin and they'll eliminate damage. So what will happen to our material properties? Alright. First of all, which material property do we care of for reactor pressure vessel? Now, for this, we care about the ductility and brittleness. So we want to know whether it will have a ductile versus a brittle structure, a brittle property. And we hope that if the material fails, excuse me, if the material fails, we want it to have a ductile failure so that it doesn't rupture all at once. We kind of see it bulge a bit, we kind of see it leak a bit before it breaks. So that is a sign of warning before failure. As my professor who taught me would have said it, it's important to emphasize leaking before breaking. Okay, leaking before breaking. So thank you, professor. So we tend to want our material to be relatively ductile. So how does radiation affect ductility? How does radiation affect ductility? For this, we need some prerequisite knowledge. If you're not sure, please pause the video and familiarize yourself with some of the knowledge I'm listing out now. And some of the helpful links will be in the description below. Stress strain curves, we need to know ductility and brittleness and how dislocations cause them or affect them. We also need to know work hardening, or rather how alloys cause hardening and why. And we also want to know about work hardening, frenkel sources, and etc. You may also want to know what an Orowan, let me see whether I got spelling right. Yeah, okay, it's called Orowan Mechanism. You want to know what all these things are. So if you're not sure, don't worry, go and see the video below. So I assume you know all this already. So first we know that ductility is easily described by how easily dislocations move through a lattice. How easily dislocations travel through lattice. Now with more obstructions to dislocation motion, the harder, when we have more obstructions to dislocation motion, the material will become harder and more brittle. Some of the prerequisite knowledge here are described already. So our stress strain curve, normally when you harden a material, let's say you have a ductile material like that. So this is stress versus strain. So you have this linear region, which is the elastic region. Then you have a ductile plastic deformation, which is characteristic of this region here. And this is where it ultimately fails. But for a, let's say a hardened material that's brittle, it may be more stiff, the yield strength may be higher, but it will start to fail like this. Brittle failure. Okay? Now what about radiation hardening? Radiation hardening may look something like this. Maybe I'll use a different pen. Radiation hardening may look like this. Notice that there is a curve downwards. Okay? Why does it do this? Why does the stress versus strain suddenly take a nosedive? Well, it's because of the nature of the hardening agents. Now, let's say we have pure iron versus, let's say, iron and carbon alloy. So, pure iron, steel alloy. Okay, in steel we will have some impurities, carbons inside. So for iron, when this location travels through a perfect crystal, it won't see any kind of obstacle, so it's relatively soft. Excuse me. But when it goes through steel, it starts to see these kinds of precipitates here, either carbon or something else, or even individual atoms. All of this will tend to stop the dislocation motion. And that's why for steel, it's slightly harder. The yield strength is higher, and also you will have Young modulus increase. So E stands for Young modulus. The Young modulus will increase, and usually the stress strain curve will be a bit stiffer, though you'll still have a plastic deformation, but it will tend to be more brittle as compared to pure iron crystal. Now, if we stretch our material via cold work, okay, okay, just to recap, every time a dislocation travels through some precipitate, okay, it will travel through some precipitate, it will start to loop around the precipitate, and then it will form like loops here. When it so this as it there's a stress in this direction, or rather, yeah, there's a stress pushing the dislocation in this direction. They will tend to wrap around incoherent precipitates. So incoherent means anything the dislocation itself cannot cut through. Okay, so when it wraps around the incoherent precipitates, there will be more dislocations forming around this precipitate. And as every time you kind of pass dislocations through this area, there'll be more and more loops that are forming. Okay, and remember Frenkel mechanism, where you have two fixed points holding down dislocations. So when there's stress, again, the dislocation moves in this direction. It will stretch and bulge out a bit. And then it'll start moving around. Okay, and as we have stress in this direction, and then after that, you will have originally this two pinpoints that hold down the dislocations, and then we will have like one loop here. So every time you push stress through this area, you apply stress through this area, and dislocations kind of form like this. There'll be more and more dislocations like this, and every time a dislocation outside sees this loop, they will say, oh, I need to wrap around this. So there's an extra obstacle. Extra obstacles made with incoming dislocations. So extra obstacles to dislocation movement is made with incoming dislocations. So yeah, we can look at the Frank Reed videos. However, for our irradiated sample, okay, for our irradiated sample, okay, we have lots of obstacles also. Let's say we have a vacancy, we have interstitial, all these kind of things, blah blah blah. When a dislocation comes in, when it sees a vacancy, what will happen? Remember that when a vacancy sees an extra plane of atoms, it tends to absorb into that. So when a dislocation comes in, it will tend to absorb vacancies, it will tend to absorb interstitials, it will tend to absorb defects that are made up of either of these if it's energetically favorable. So as these locations travel through, suddenly all the obstacles to this location are gone. No obstacles. So this is known as irradiation softening. Okay, just ignore this. Irradiation softening. So it means obstacles disappear, so to speak, as dislocations move through. So when dislocations are moving through this irradiated sample, it's not really that radiation directly causes a softening effect, but rather it's because radiation leaves behind all these vacancy and interstitials and similar defects, and these defects can be cleaned up by this dislocation movement. So yeah, for relatively, let's say, pure iron, not exactly stainless steel, you can see that radiation tends to harden materials because the first time the dislocation travels through it, there will be obstacles and there will be extra force needed to push it through and cause all these to absorb into the dislocation. But after that, we don't have any obstacles there. So this is irradiation softening. So in summary, we know that our material will become more brittle, it will have a higher yield strength and a higher Young's modulus, as we can see, and we know why. It's because of barriers to dislocation motion. Yep. And we know why it will tend to soften after a while. And but nevertheless, the toughness, the area under the curve, is a lot less and it takes less energy to break. So the overall toughness also decreases. However, we have not considered yet how this affects materials when there are mixtures of materials, how irradiation affects materials when there are mixture of materials in the system. So far, we have only talked about vacancy and interstitial when it's only one type of atom inside the lattice. What about if there are a mixture? Let's say if there's copper or helium. How does that affect our steel? Find out in the upcoming videos. So thanks for watching. I'll see you guys next time. Bye bye.